Kirchhoff's current law, or KCL, applies to currents going in and out of a node. But before I go to the details of the law, I need to make sure that we understand what a node is. So a node is simply a point where two or more elements meet. So let's assume we have an element, whatever that is. It could be a resistor, sources, and you have another element. And of course, each one of them will have a couple ports. And what you do is you go and you connect them. By connecting them, you created a node. The node also might have more elements connected to it. So if you have a third element in here and you connect it to this node, it's the same node. We just call it a node. So basically it's a point where a bunch of elements, two or more elements, just meet. So I want to make sure you understand the concept of a node. So I'll just basically explore a few circuits in here, or a couple of circuits, and we'll define the nodes on it. So let's identify some of the nodes in here. Well, we'll start with this circuit in here, and let's define a node. Well, we have a resistor that meets here. It meets with a current source. So then, well, that's a node, and I called it 1. And it just happened to be that this particular node is also connected to this particular resistor in here. So we have defined a node in here. Okay, well, the node is also here. It's the same place. So this node is the same as this node in here. It doesn't matter where you keep that particular node. I'll highlight it. Let me just make sure that we emphasize. It doesn't matter how we draw that node. The whole thing in here, from here all the way to here, all the way to here, since there are no elements on it, it's just a wire, the whole thing is a node. And I can redraw that circuit, and you will see it shortly that these two circuits are equivalent. They're the same exact circuit. But what we did is, instead of drawing that source with this particular angle and this resistor with this particular angle and just connect them in here, you'll see in this particular circuit, the R2 is connected in here, R1 is connected in here, and this particular current with the same direction is connected in here. So as it turns out, this node and this node are exactly the same. So this is node 1. It's exactly the same. So it doesn't have to be an angle. Just make sure that I emphasize. It doesn't have to be an angle. This is not a node that is separate than this node that is separate than this node. They're all exactly the same node. And you can redraw the circuit just to make it this way. And you can identify other nodes as well. So let's take a look at 2 in here. So 2, what does it combine? Well, it combines the following two. It combines R3, R4, and the IT. So R3, R4, and the IT. So this particular node is actually here. So it's the same exact node. And again, I can highlight the whole thing in here. This is a node. This whole thing is a node. And I can highlight it in here. This whole thing is a node in here. All right, let's highlight another node with a different color maybe. So what we have is we have node here. This is node 5. So the whole thing in here, the whole thing in here, the whole thing. This is a node. And if I redraw it, you will see that it is the same one in here. But typically, you'll see me just identifying a node, something similar to this, and I'll tell you this is a node in here, and that's about it. It's basically where a bunch of elements meet. All right, so that we know what a node is. Let's define what KCL is, or what does it do? Well, KCL simply says if you have a node, and in this particular node, you have a bunch of wires connected, of course, like a bunch of elements connected to this particular node, and it doesn't matter how many of them there are. Maybe you have I1 in here. Let me just do this here. Maybe you have I1 coming out, and maybe I2 is coming in, and maybe I3 is coming out, and maybe let's say I4 is coming out of the node, and maybe I5 is coming into the node. So what KCL tells me, like, you have all these currents meeting in a node. Well, as it turns out that the current actually splits and merges, and KCL simply states that the sum of the current entering a node should be equal to the sum of the current leaving the node. So let me just rewrite it here. So the sum of the current entering should be equals to the sum of leaving the node. Okay, the current leaving the nodes. Okay, so let me write it algebraically. Well, I have to identify which ones are leaving and which one are entering the node. So I5 is entering the node, I2 is entering the node, and I believe these are the only two currents entering the node. And if I see I4 and I3 and I1 are leaving the node. So simply, I have to say, well, entering the node is here. I have I2 plus I5, and KCL tells me this is equivalent to I1 plus I3 plus I4. That's what current KCL tells me. It's just straightforward. It tells me the sum of the current, basically the currents going in, the sum of the current going in equals to the sum of the currents leaving. Frankly speaking, it wasn't formulated this way. The way that KCL is formulated is the algebraic sum of all the currents going in and out of a node should be equal to 0 because that's basically conservation of current. But anyway, so if I rewrite this, I can just rearrange all these terms, and you will see if I define that the current leaving are positive. So let's assume that I said, well, the currents leaving the node, I'm going to assign them as positive, and the ones entering, I'm going to assign them as a negative sign. So I can simply say, well, okay, I1 is leaving, okay, so I'm going to say I1. Well, I2 is entering, so I'm going to say negative I2, and I3 is leaving, that's I3, and then I believe leaving as well I4, and then 5 is negative I5, and this is equal 0. So these two equations are equivalent. So either way, they're equivalent. They're both KCL for the same particular node. You can either formulate it as a sum of current equals 0. You decide whether leaving is positive or negative. It doesn't matter as long as you're consistent, because at the end of the day, it's algebra. I typically prefer just to use the sum of currents entering equals the sum of current leaving the node. All right, now we know what KCL is. Let's see how it will help us figure out the equations, or write equations to solve this particular circuit, the one that we've seen in a previous video. Okay, well, in here, I have to first define what nodes are, or I can find nodes. For example, I can find this is a node because I know that the source and the resistors are meeting. I'm going to call it node A. This is another node. I'm going to call it node B. And this is another node, and I'm going to call it C. So I'm going to write an equation, or KCL equations, for each one of these nodes. So I'm going to focus on A first. So at A, let me just do that here. So at node A, okay, this one here, I have the sum of the current entering equals the sum of current leaving. So I simply can say, well, I of S equals I of 1, because the I of S is coming in and the I of 1 is leaving. So, which is straightforward because I see it like we've seen it before in a single loop circuit. It's the same, well, it's the same current going through this element and this elements because they're connected in series. All right, what about the other nodes? So let's see another nodes in here. Okay, so let's say the node B. So at node B, I have I have I1 coming in, and I believe I2 is coming in, and I3 is leaving. So I can simply state it as I1 plus I2 equals I3. And at the last node, which is C, I will just say, well, I3 is coming in, and I2 and IS are leaving. So I can say I2 plus I of S equals I3. So I have now three equations. As you guys remember, or hopefully you remember, that we needed 4 different equations in order for us to solve this circuit, in addition to whatever Ohm's law gives us. And as it turns out, without proof for now, as KCL, these 3 equations that we got, only 2 of them are independent. So you only need 2 to generate the third. So you can, for example, if you wrote only these 2, you will be able to figure out the I1 equals I of S later. So technically, KCL gave us 2 different equations. So we have 2 equations out of these. Okay, so 2 out of 4. So that means we need an additional 2 equations in order for us to figure out or solve the whole circuit. And here's where KVL comes in, Kirchhoff's voltage law.